Hi, I'm Weijia, a PhD student at the University of Groningen, the Netherlands. I'm presenting distributed coordinated path following using guiding vector fields. I'm going to start my talk with a story. In the Netherlands, when you fly a drone, you need to be very careful because I think the chimpanzees make it clear that they don't like drones. Autonomous drones shouldn't get stuck or they are vulnerable to attacks from chimps. So they should try everything they can to avoid singularity areas in guiding vector fields, especially in the case of multiple drones. So what is a guiding vector field? What do I mean by singularity areas? I will explain now. Following accurately a desired path is a fundamental task in mobile robotics. So the path following problem is a classic problem, and there are many single robot path following algorithms. We are especially interested in those based on a guiding vector field. In this picture, a fixed-wing aircraft flies by following the arrows at each point. These algorithms can achieve high path following accuracy and have been used in many practical applications such as fixed-wing aircraft guidance and control. We can summarize our work in one sentence. We propose a singularity-free guiding vector field that enables distributed, multi-robot coordinated motion along general desired paths in n-dimensional spaces. For mobile robots, n equals 2 or 3. For robotic arms, n is the number of joints. N is also related to the number of virtual coordinates as discussed later. We achieve this with rigorous mathematical guarantees. Next, I will introduce what a guiding vector field is. In guiding vector field-based path-following algorithms, the desired path is usually described as the zero-level set of a smooth implicit function denoted by phi. Here is an example in 2D. The guiding vector field is determined by the implicit function phi. Tree denotes the vector field, which gives an arrow at each position xy, and it changes its direction and magnitude continuously with respect to the coordinates. This is the rotation matrix, which rotates the gradient vector by 90 degrees. K is a positive constant. To understand what these terms mean, we draw each term now. This picture shows the gradient vectors described by nabla phi. Rotating all the gradient vectors by 90 degrees, we obtain this one. Note that the vectors are tangent to the circle. This term is the gradient multiplied by minus k phi, which makes all the vectors point orthogonally towards the circle. Adding these two terms, we obtain the guiding vector field for the circle desired path. Then the robot's motion following the guiding vector field is the solution to this ordinary differential equation given an initial position. A trajectory is animated here. Given a desired path living in an n-dimensional space, we can similarly derive an n-dimensional guiding vector field with the same structure. That is, it consists of a tangential component and an orthogonal component, but we do not go into the details here. Next, we introduce singularity points. A singularity point is a point where the vector field becomes zero. The red points in these pictures are singularity points. They may be isolated or connected to form an area. Singularity points are undesirable. If your drone gets stuck at this point, it is more vulnerable to attacks from chimpanzees, and no global convergence of trajectories to the desired path can be guaranteed. Worse still, we prove that there is a topological property. If the desired paths are closed or self-intersetting, then there are always singularity points in the guiding vector field, no matter what implicit function phi you choose, and no matter what the dimensions of the space are. One may assign arbitrary non-zero vectors to these singularity points, but this would make the whole vector field discontinuous, which is not desirable. So a fundamental question is, can we remove this singularity point while maintaining the continuity of the vector field? The answer is yes, but how to do that? The solution is to do a topological surgery, which transforms the initially closed or self-intersetting desired paths to become open and infinite by cutting and lifting the desired path to a higher dimensional space. To demonstrate this, we assume that the desired path is a circular elastic stream in the xy plane. We use scissors to cut it, then pinch the two ends and stretch it vertically. The 2D circle now becomes a helix in the 3D space. Now we have an additional dimension along the w-axis. Therefore, we can obtain a 3D guiding vector field corresponding to the 3D helix. For clarity, we select 3 slices at different w values and plot the vectors starting from each slice. At different W values, we also plot the projected vector fields onto the XY plane. If we look at these projected vector fields, they are no longer static but changes dynamically as W changes. It can be guaranteed that there are no singularity points anymore. Now we show how to use the new dynamic vector field in practice. On the left is the actual robot motion into 2D XY plane, and on the right is the virtual robot motion in the 3D space, where the W-axis is the additional dimension of the space. The red points represent cosine W, sine W, which reflects how W changes. This point is different from a trajectory point in trajectory tracking, but we omit the details. We can see that the vector field is dynamically changing as the position of the robot changes. This dynamically changing vector field is actually the projection of the 3D vector field, and the 2D motion is the projection of the 3D motion on the right. We have created a singularity-free guiding vector field for a single robot. Now the second question is how to extend it for multi-robot coordination. Before we go to the technical details, let's see the example of 6 robots moving with or without motion coordination. We want these robots to move along a circle and also keep equal distances to each other. One might be tempted to directly use the original 2D static vector field and let 6 robots follow the directions given by the vector field. But in this example, they cannot keep equal distances as desired. In fact, their trajectories and the inter-robot distances are determined by their starting positions. Also note that the red robot does not move at all since it gets stuck at a singularity point. We propose to use the singularity-free guiding vector field introduced before and let the neighboring robots share the virtual coordinates W by communication, as shown by this graph. Starting from the same initial positions, these 6 robots follow the circle while keeping equal distances. Let's see what is behind the scene. On the left, these 6 robots move according to their respective guiding vector fields, represented by arrows of different colors. On the right, for clarity, only parts of the vector fields around robots are shown. In fact, the coordination is achieved via local communication on neighboring robots' virtual coordinates, and the changing virtual coordinates affects the guiding vector fields, which then guide the motion of robots. Next, we show the technical details. Remember that W is not only a virtual coordinates, but also the path parameter. So coordinating the virtual coordinates W is equivalent to coordinating the positions of the robots. Take the 2D desired path as an example. This equation is the coordination guiding vector field for multi-robot systems. To be more specific, this term is the 3D singularity-free guiding vector field we discussed just now, and we add another term called the coordination term, scaled by a positive constant Kc. The combination becomes the coordination vector field. Note that the first 2 entries of the coordination vector field are related to the physical x and y coordinates, while the last entry is virtual. Therefore, the first 2 entries in the coordination term are 0 because the coordination term would better not affect the physical x and y coordinates directly. Instead, we only control the 3rd entry, which is the classic consensus algorithm. That is, it equals my virtual coordinates Wi minus my neighbor's virtual coordinates Wj minus the desired difference between the virtual coordinates delta ij. Then these are summed up over all my neighbors. In the previous example with 6 robots, the actual difference in the virtual coordinates Wi minus Wj and the desired difference delta ij converges to 0 as shown in this picture. So the coordination is successful. Note that the coordination vector field is not a gradient of any potential function, but we can still guarantee the convergence to the desired path and the motion coordination from all initial positions. We use the guiding vector field for not only the single integrated model, but also other robot models. Here, the fixed-wing aircraft is modeled by a dubious car. We can use the Lyapunov theory to design the 2 control inputs, UIZ and UIθ, such that the fixed-wing orientation is eventually aligned with the arrows given by the coordination guiding vector field. The control inputs are shown here, which also consider input saturation. Please refer to our paper for more details. In this experiment, we want the virtual coordinates of 2 fixed-wing aircraft eventually become identical. On the top left is the visualization of the telemetry data. The The red and blue arrows around the aircraft are part of the guiding vector field. On the top right is the ground control station. As we can see, the two aircraft, although starting from two different locations, eventually fly together on the self-insetting 3D path. The video at the bottom is the actual flight of them. All codes are open source in the Autopilot Paparazzi website. Another application is covering a 3D volume. Here, the magenta curve is the desired path, a Lissajous curve with irrational coefficients. It is open but bounded in a cube. Therefore, the robots can cover completely the cube. The second application is coordinating robot motions on different desired paths using the path parameter. We can further extend our algorithm to enable robots to converge to any surfaces and coordinate their motions. In this video, 67 robots form a pattern and also maneuver on the torus. Perhaps you may wonder how these robots can avoid collision with each other. Although this is not the focus of our work, we briefly demonstrate here that our algorithm can be combined with a safety barrier certificate to avoid collisions. In conclusion, we propose a coordination guiding vector field for multi-robot distributed path following. There are many appealing features in our approach. First, it is distributed and scalable, and thus applicable for a team of an arbitrary number of robots. Second, it enables following of complex paths such as self-intersecting, non-convex and non-closed ones. Third, the communication burden is low since every two neighboring robots only need to transmit and receive one scalar, the virtual coordinate. In addition, the algorithm can be used in real-time applications with low computational cost. There is no need for online optimization. Fourth, it is singularity-free and has global convergence guarantees. We validate our algorithm with fixed-wing aircraft, which are modeled by saturated Dubin's cores. Thank you for your attention.